In our next section, we're going to review the BGP EVPN configuration for VXLAN and talk about what are some of the advantages of using this design as opposed to the previous one with flood and learn, which is ultimately going to lead us into some more of the advanced options here in terms of the layer 3 routing over VXLAN, the Anycast VPC, and then some of the other minor optimizations that we'll see that BGP brings to the table that we don't have available when we're talking about VXLAN flood and learn. Now, the ultimate goal that we're trying to accomplish here is that instead of simply receiving the traffic in from the end host and then basically just broadcasting it out to the fabric in the middle, we're trying to use BGP as some sort of active mechanism to map two things together. Okay, the MAC address to the VXLAN tunnel endpoint, and then the IP address to the VXLAN tunnel endpoint. Okay, this is the design that we call the layer 2 VXLAN network identifier, or the layer 2 VNI, and the layer 3 VXLAN network identifier, or the layer 3 VNI. Okay, layer 2 VNI, hence the name, is going to be used for layer 2 switching or layer 2 bridging across the tunnel. Layer 3 VNI is going to be used for layer 3 routing, where the source and destination are in different subnets. Okay, but before we can talk about the layer 3 VNI, we need to make sure that we're clear on the protocol mechanics of what BGP is doing behind the scenes. So what's going to happen is that we're first going to be learning the MAC address of the server. So we have server 1 that's physically attached to 5K1. So from its point of view, it's going to know that the MAC address of 1111 is reachable out that particular port. And then we're going to send this information as a BGP L2 VPN, EVPN advertisement somehow towards the other remote leaf switch, okay, which in our case is going to be 5K3. 5K3 is then going to know, hey, if I want to reach that particular MAC address, I'm going to go to the VXLAN tunnel endpoint that is the loopback address of 11151, okay, or whatever IP address that that box has configured. So instead of doing learning in the data plane, like a regular Ethernet switch would do, that it receives a frame in and just sends it out everywhere, we have an active mechanism that's running behind the scenes that's doing that mapping for us. So essentially what we're doing is like offloading the ARP cache into BGP as opposed to having the traffic just go everywhere in the data plane. So this is going to become more efficient once the network starts to grow. It is, of course, going to add complexity because we have additional control plane, we have additional configuration that's needed behind the scenes, where the flood and learn, simple from a config point of view, complicated from a scaling point of view. BGP, the opposite. Simpler from a scaling point of view, but more complicated from a configuration and then an operations point of view. Okay, so our config steps are going to be the same to start as we saw with the flood and learn. So first we map our VXLAN to our VLAN, which is the VN segment command under the VLAN config. We specify our tunnel interface, which is going to be interface NVE, and again this should say interface NVE1. We specify what the source address is, so it's going to be our loopback. We're assuming that we already have IGP reachability to that, which in this case we're running OSPF between the leaf and the spines. We then specify what VXLAN network identifiers are going to be part of the tunnel. So that's going to be depending on your local members that you want to bridge towards. Then we're going to specify what multicast group we're using for broadcast and unknowns. Okay, so we're still going to need multicast transport in the core, and we'll see why in a minute here. Why do we need multicast when we're using BGP for the control plane? Going to have to do with silent receivers. Okay, then the other change here at the NVE tunnel is we're going to set the host reachability protocol to BGP. So up to this point, only one command difference versus the flood and learn versus the BGP EVPN. Now, of course, there is going to be additional BGP configuration where we're going to have to do BGP peerings, and then we're going to have to activate that specific address family identifier and the sub-address family identifier, the AFI being layer 2 VPN. The sub-address family identifier is EVPN, or the AFI, the AFI-SAFI pair, which would be the equivalent of like saying IPv4 unicast. Okay, it's a type of advertisement that's going between the neighbors, and we need to make sure that they agree upon this in their capabilities exchange before we can build the BGP peering. Now, in most typical designs that you would see with BGP for VXLAN, since we already physically have the networks set up as leaf, spine, leaf, the spines are already in the data plane. which makes sense to also host the control plane for BGP on them, or in other words, we're going to configure them as BGP route reflectors. So in our particular case, we're going to have everybody peer with our two spines, which in this case are 7K1 and 7K2. So these are going to be our route reflectors. And then the reflectors are going to be peering down to the loopback interfaces of all of the leafs. Now we'll see an important point here is that when the route reflector receives the route in and advertises it back down to the remote leaf, it is not updating the next hop value. This means that when 5K1 sends a route to 7K1, 7K1 sends it to 5K3, 5K3 sees the next hop as the loopback of 5K1 as opposed to the spine. Okay, we'll come back to that later when we look at inter-fabric reachability. So we have multiple separate control planes that we're combining together with eBGP. If we use external BGP, that is going to be a consideration we need to think about is what is the next hop processing to make sure that we're using the correct VXLAN tunnel endpoint. Okay, but with iBGP and route reflection, it doesn't change the next hop by default, so that's not going to be a problem. Okay, so once we establish the peerings, then we're going to specify what advertisements do we want to send into BGP. This is the EVPN configuration mode. You can think of this like the network statement under BGP. So I'm redistributing the MAC address table that is part of VNI 11111. Okay, then the route target and the route distinguisher, we'll talk about these a little bit later when we look at the details of the eBGP reachability for the interfabric. Okay, for our first example, we just need to say auto for all three of these, and it's going to take care of it automatically. Okay, so let's go ahead and modify our config. So we're going to start on the spine switches. So let's go to our 7Ks here. And their config is going to be basically identical. Now, the last time we did this config, I had manually specified the peerings that were going down to all of the leafs. The disadvantage of that is that as you add more leafs, you have to update the config of the reflectors. So what I'm going to do in this case is to use BGP dynamic peers and show an application that makes it a little bit more manageable from an operations point of view in a real deployment, where when you add new leafs, you don't necessarily need to update the config of the reflectors. Okay, so in global config, we're going to turn the feature NV overlay on. Okay, the reason why, if we don't do this, if we go to feature BGP and then router BGP, whatever our AS is, let's say 1, 2, 3, 4, 5, and then we look at the address families, if we go to L2VPN, notice that even though that's in the context-sensitive help, it doesn't let you go to the sub-address family identifier. Okay, the reason why is that the feature's not on. Okay, the feature specifically is feature NV overlay. Okay, now if we go to router BGP 1, 2, 3, 4, 5, address family, L2VPN question mark. Actually, we need to go into the neighbor. Neighbor 1, 2, 3, 4, address family, L2VPN, feature NV overlay. Actually, no, two commands. Feature NV overlay and then also NV overlay EVPN. So router BGP 1, 2, 3, 4, 5. Address family L2VPN, EVPN. Okay, so two features that need to be enabled on everybody now, both the leafs and the spines. Feature NV overlay and NV overlay EVPN. Okay, so let's say show run pipe include NV, and then we're just going to paste this on the rest of all the boxes. Okay, anybody running BGP, L2VPN, EVPN needs these features. Okay, so we're under the BGP process, router BGP 1, 2, 3, 4, 5, and we're going to say the neighbor, and instead of specifying the individual IP address, if you notice in the question mark here, there's an option in Nexus for a subnet mask. In the case of regular iOS, they call this BGP dynamic peers, or it's the BGP listen feature. So what I'm going to say here is that any address that starts with 1110/24, I'm going to be listening for a peering to come in. Okay, that's the reason when I specified my loopback addresses, I had them come from the same major network. Okay, the major network in that case was 1.1.1. And then we had .51, 52, 53, etc. So we can group them all together in a kind of like a clean summary range, and then use this as the address pool essentially that we're using for the BGP dynamic peering coming into the spines. Okay, so we're going to listen for this. So let's say under BGP that we're going to log neighbor changes. Okay, so neighbor is 1110/24, and we're going to say the remote AS is 12345. Okay, so they're iBGP peers. Update source is loopback 0, so it's loopback to loopback. The address family is going to be L2VPN, EVPN. We need to send communities, and we need to send extended communities. Okay, now we could send both if we were trying to do some community marking. It's probably best practices to do that, just in case later down the road you want to do some sort of traffic engineering with BGP, and you're doing that based on tagging the community onto the prefix. But at a minimum, you must include extended communities. The reason why is that the VNI and the route target are encoded as extended communities onto the actual route. Okay, without that, the route will be exchanged, but you won't be able to send traffic to the destination because it won't get installed into the routing table. So from a troubleshooting point of view, this could be one way that could be easy to screw up the config, is that all the peers are established, but if extended communities are not exchanged, it's not going to work. Okay, let's show run BGP. And essentially, that's it. Okay, so let's get rid of this guy. No neighbor 1234. Show run BGP. And we're going to do the same thing on the other side. So let's enable logging on everybody. Okay, then 7K2 says the exact same thing. Feature BGP. Okay, which will say that on everybody. Feature BGP. And then we're listening for the peers. Now from the Leaf's point of view, their config is going to be 100% identical because we have the same spine neighbors or the route reflectors that we're trying to peer with. Okay, so I'm going to build this on one of them and then we'll just copy and paste it on the rest. So we'll say router BGP 12345. We have the neighbor that is 11171. Okay, that's the first reflector. The remote AS is 12345, and actually now that I'm thinking of that, the reflector, okay, I'm missing one command, is under the address family. I need to say that these guys are going to be route reflector clients. Okay, so that goes on the 7 case. Okay, so 5K1 is saying the box is in the same AS as us, 12345. Update source is going to be the loopback. Okay, let's also log adjacency changes or log neighbor changes. So we have the neighbor, and then the address family is L2VPN, EVPN. Send community, both. Okay, then for verification, we can see the neighbors up. Okay, verification, we're going to show BGP. Our address family identifier is L2VPN. Our sub-address family identifier is EVPN, and we want to look at the summary of the peering. Okay, so show BGP, L2VPN, EVPN summary. Okay, we see we have the peering to 7K1. If we show run BGP, we're going to do the exact same thing, but we're going to do it for the other neighbor. So we'll say neighbor 11172, and then just paste the same config back in. Okay, we should see on 7K2 that we get a log here. So let's show BGP, L2VPN, L2VPN, EVPN summary. And we have 11151. Okay, if we look at the neighbor specifically, let's say show BGP, L2VPN, EVPN neighbor 11151. What it should tell us about this guy is that this is a dynamic neighbor. Okay, so we don't have a static peering configured for them. The end result is ultimately the same. It's just that we don't need to statically configure the address. Okay, so it's kind of like IGP where you configure it on both sides and they auto-discover the neighbors. With BGP, you have to at least define the neighbor statically on one end because it's originating the TCP session. Okay, once the 7K gets the TCP SYN, so the start of the three-way handshake in, it knows who to reply to, and then it can complete the session. But this makes it a little bit simpler because now on the leaf, if we show run BGP, we can literally just copy and paste this exact same config on the rest of the leafs, and the peerings are going to be complete. Okay, so 5K2, 5K3, 5K4. And then if we look at the spines, show BGP, L2VPN, EVPN summary, we should see that the rest of the peerings are going to come up there. So 5K2, 5K3, and 5K4. Okay, so all 4 of them are peered. Okay, same thing should be true on 7K2. Show BGP, L2, VPN, EVPN, summary. Okay, final step is we're going to generate the advertisement. So again, advertisement is going to go under the EVPN config mode. So it's in global config, then EVPN, and we specify what VXLAN network identifiers that we are specifically advertising. Okay, before we do this though, let's go back to our data plane capture. Okay, remember we're capturing everywhere and then we're dropping the frames off on 5K2's link to server 1. Okay, the capture is happening in and out the links from the leaf to the spines, and then likewise the leaves from the spines back to the leaves. Okay, so basically in both directions everywhere. So let's go to server 1. And let's start our capture. Okay, and we want to look for, let's say, BGP or ARP. Okay, so next let's do our advertisement. So we're going to go over to 5K1. Okay, you can see they're still trying to reach the gateways, but the gateways aren't yet configured because we haven't done the layer 3 VNIs. So let's go to global config. We're going to go to EVPN. And if we show run VLAN, okay, show run section VLAN, the VNI we're using is 11111. Okay, so under EVPN, we're going to say VNI 11111, and this is a layer 2 segment. Okay, the reason why we'll come back and later talk about. Okay, under the layer 2 VNI, we need to specify what's the route distinguisher and the route target. For this example, we don't need to worry about the details of this. The process is going to take care of it automatically to make sure that these values match on both of the leafs so that they receive each other's routes. Okay, but this is going to be based on your BGP AS number, and it's also going to be based on the VNI number by default. So we'll say route distinguisher is auto, and the route target is auto. Okay, import is auto, and export is auto, already auto. No VLAN ID configured, unable to generate the auto route distinguisher. No VLAN ID configured. Show run EVPN. Section EVPN. Oh, the reason why is under the NVE, I didn't specify we're running BGP. Okay, so under interface NVE1, we'll say host reachability protocol is BGP. Okay, so if we show CLI history, unformatted, pipe to show me the last 20 lines. So we're going to do the same exact thing on 5K3. Okay, if we look at the capture, we now see we have these BGP updates. Okay, BGP update came from 5K3, it was going over to 7K1. If we look at the details of what specifically is inside of this, we have the original IP packet that's encapsulated inside of Ethernet, and then Ethernet's going inside the span session. Okay, so this is not a VXLAN packet, this is just a normal BGP advertisement. It has additional encapsulations based on the way that I'm capturing it, but it's not inside of a UDP tunnel. Okay, it's just BGP point-to-point unicast between the two neighbors. Okay, so it's a BGP update from 5K3 going to the spine. Okay, it's leaf to spine, 5K3 to 7K1. Inside the update message, specifically what this is going to include is in the path attributes, in multi-protocol reach, the network layer reachability information, that's the actual route. The actual route is going to be the network layer reachability information, which is a MAC address, and the MAC address being this guy here. Okay, this 7679, if we go over to server 3, okay, which is the box that's attached to 5K3, and let's look at the ipconfig/all. We should see on the link that we have the 11.00.13, its MAC address is 7679. Okay, so we go back to our packet capture, we should see that it's this particular field, which is here, 001B21967679. So instead of advertising an IP prefix like you would do with normal global BGP routing, like internet routing, in this case we're advertising the MAC addresses. Okay, what we're advertising in addition to the MAC address that is important is two things. First is, what VXLAN tunnel endpoint does the route belong to? Okay, or does the MAC address belong to? So this is going to be in the attributes of the next hop value. Okay, path attributes, we'll have the flags, and then, let's see, where is this listed? Okay, it also tells us we're using VXLAN encapsulation. And then the route target value tells us what's the BGP AS, which is 1, 2, 3, 4, 5, and then the VXLAN network identifier is 11111. Okay, but somewhere in here, it should have been, it might be in the previous message. This might be split between two different packets. But it's going to be advertising that the next hop is 5K3. Okay, we could also see this based on the route distinguisher, but technically that's not the next hop. I don't know exactly where it is in there. Yeah. Okay, so if we go to 5K1 though, and we look at the show BGP, LTVPN, EVPN, we're now going to see the MAC addresses. Okay, so all zeros, 1111, that's server 1. This 7679, this is the one that's coming from 5K3. Notice here that in the advertisements, it's including the next hops, which are the loopbacks of the VXLAN tunnel endpoints. So now we know that, hey, if we want to send traffic to that destination, put it inside a VXLAN tunnel and then ship it over towards that particular next hop. Okay, so route the packet over to 5K1 or to 5K3. Okay, so if we were to look at now from a packet capture point of view, just the actual data plane. Okay, so let's say we're going to capture just ICMP. And we now go over to server 3, and we do a ping to 11.00.11. Okay, that's server 1. We can see we have reachability to it. And if we look back at the packet capture, we have the echo going out, and as it's going out to the fabric, so this is 5K3, that's routing it towards 5K1. We have the inner IP packet, which is the ping between the two servers. We have the inner Ethernet header, so it's coming from server 1, it's going to server 3. We're then saying it's in this particular segment. It's in VXLAN network identifier 11111. We're then putting it inside of a UDP packets, destination 4789. And it is then unicast routed from 5K3 over to 5K1.